you like hopefully don't remember. So that's the gap. That's the problem between how much we are using AI today and how little we are aware of what we are feeding to it. And I think that's the problem we are going to talk about today and its potential solution as well. So, like every day companies are sending their customer data, their financial details, their internal insights into AI models. And the problem is that like everything is happening so silently that, we don't have any alerts, we don't have any visibility, we don't have any control to it. And as we all know that AI is, driving productivity, no questions to it. But it's also, introducing a new kind of security risk that most organizations haven't been able to find it, or else like if they have find it, then also they are not even able to name it properly. So today we are going to talk about that risk, and actually how that risk actually builds and looks like, and what we can do about it. So when the first AI entered to the enterprises, the focus was completely different. Where the agenda for board meetings were mainly around models, workflows, context size, and managing memories. And they were valid discussion topics, and they still are valid, but they are no longer the first thing that gets discussed when now AI is matured. And the first one that gets the most attention today is in every board meeting, every architecture review, every compliance meeting is security. Enterprises are no longer asking how powerful AI is. They are now asking that what information we are passing it to the model, what we are exposing to the models. How do we stay compliant with policies like GDPR when AI has memory attached to it? And now security is not something that we add later. It's the first decision that we have to make before designing any AI system. And just a fun little element over here. I don't know why the organizers have kept this security session at the end of the day. It should be the first one. But again, just kidding. They're doing their job great, and huge respect for them. But and on that note as well, like not a long ago, just a month back, I was reading an article in the Economic Times, and the number really, stopped me and forced me to think that nearly 40% of the enterprise decision makers, they are really worried about sensitive data getting exposed to external systems. And around 25% of the CIOs, they believe like AI deployment like usually impact the data control and the governance aspect. And most importantly, data privacy is now the biggest barrier when it comes to scaling the AI. So this isn't just the problem on the paper anymore. This is already happening in the organizations. And there is another layer to it as well that I feel doesn't get much attention is, as we know that geopolitical tensions keeps on rising across the countries, and even companies are becoming far more protective about where their data goes, who processes it, and under whose control the data is sitting, which means sending sensitive data blindly into AI systems. It's not just the technical problem or a problem that can be solved with technical approaches. It's the business risk, it's a compliance risk as well. And together with that, it's a geopolitical risk as well. So that's the gap we are, trying to talk about today. Now, when we talk about security risk in enterprise AI, it not always comes in just one form or one flavor. The risk surface is really, really wide, and it comes in multiple ways and at multiple different stages. So, it would be in the form of data leakage. This is the one we are going to focus on today, where, sensitive data leaves your boundaries to the other system via AI conversations that we do daily. And the scary part is like we don't get any notification when we leak the data. As in like most of the times we are in hurry, we just copy paste the prompts and responses here and there. And that's how, we leak the data to external systems without even realizing. Second is prompt injection. So, sometimes what happens is like bad actors, they hide some information inside the input, and then agent ends up following that instruction instead of what we have written. So your model gets hijacked by the bad actors without even they touching your infrastructure. So that's again a one sort of risk that we need to take care of. Third risk is model and training attack. So this is different because here the damage is happening before we deploy anything. So let's say like where the data on which our model is trained on, that data is itself vulnerable and it's compromised. So when we will deploy the model, it's gonna be vulnerable from the day one. So like think about it as a student. Let's say like if you are teaching a student some wrong facts from the day one, now they'll just confidently gives or circulates those facts among the groups every time and with everyone around them, as in like they think that the facts that we have shared with them are true, so that they'll just keep on circulating, but they are not true. So again, this is a kind of risk that can quietly happen at an enterprise AI. Then we have this identity and access abuse. So this one is about AI agent getting more access than they should usually. Like instead of just read, they now have the read, write, remove, delete, everything, and they can harm your systems anytime without stopping or asking you. And then finally, we have the inference and reconstruction, where in this type of risk, someone, let's say bad actor, they'll just ask the model right questions in the right sequence so that the model start revealing what it has learned during the training period. So again, that's vulnerable, and that risk is silently happens in the enterprise AI. So there are many ways this can enter and into AI systems with AI systems, but these are the five that matters the most when it comes to identifying the risk. Now let's just zoom in into the first one and see how we can try to solve that. So before we talk about solving the data leakage problem, we first need to understand the problem. Let's see how data actually gets exposed to in LLM. So just imagine one scenario. It's 9:24 a.m. Monday morning, and the CFO, calls the financial analyst, Rose, and tell her that they're having board meeting at 3 p.m. and she needs Q3 variance report. Now, Rose is, highly under pressure and she needs to, move very fast. So she does what most of us would have done. So she just, opens the AI assistant. She starts with something completely reasonable, like I need a board summary for XYZ. And, that query seems completely fine. Nothing sensitive is, nothing sensitive was there in that particular query. Then she keeps on adding context the way we naturally do in a conversation, like the deal size. Then she exposed the expected synergies, then the internal assumptions that they were having, which they have derived after a lot of research and analysis. And then without even realizing, she shares something again very sensitive over here. And like at this point, Rose feel that she was, leaking at any point. She doesn't feel like she was exposing the information to the AI conversation assistant that they were having. And but the finance team's internal, downside projection, plus their month of risk analysis, plus their, judgment, their expertise, and their, months of research, all of it were leaked in just one session. And this is just the one example from finance department, but the same thing happens every day across every regulated industries. Like let's say in healthcare, a doctor maybe putting in patients data to get a different opinion on the case studies. Let's say in HR department, a manager could be describing an employee's situation to just get the help with the difficult conversations that they are having. Where and in general scenario as well, where we just copy and paste the information to AI without even realizing as well. So in order to solve this, naturally to today, like we do have approaches like redaction, masking, encryption, placeholder. But the problem with these techniques is like either they will just destroy your data or they will destroy the usefulness with LLM. So for example, like reduction. So it simply, removes the sensitive data from the query. And for an example, like we do have this sentence. So it like entirely removed this PII information that was detected from the sentence. So let's say like if we remove the entire thing, it will, cause the LLM to lose the context. So the output quality will drops significantly. Now, second approach that we have today is like placeholder. This is slightly like smarter than the reduction, but again, similar problem. We are just replacing the entities with the labels. So this keeps the structure, but again, LLM is now responding to the labels, not the real context over here. So again, usefulness will gonna degrade over here as well. Then we have the masking. It also shares the similar problem. And additionally, it's leaking the structure of the entities as well. So via, first letter or via number of length of characters, we would be able to practically get reverse engineer and get to that particular identity. Then finally, like we have this encryption as well. So this is the most secure one, I feel. But again, like LLM can't, reason over this encrypted text. So it become, practically unusable to implement such strategies when we deal with the context and we need some personalized response. So across all the approaches, the trade-offs are clear and visible. That is, either you protect the data and you lose the utility to LLM, or you keep the utility but still keep on leaking the information to the LLMs. And none of them handles them how the way how LLM actually works today, which is context building across multiple interactions. As in today, majority of the tasks that we do requires multiple iterations. We cannot get anything in just one prompt and one response. So that's where we built a module using powers of all, where it can protect sensitive data without breaking the utility of the LLM. And we call that module as a CAMP, cumulative agentic masking and pruning. Cumulative because the risk doesn't live in a single message, as I just mentioned, that it build across turns. So consider one example, that in first turn you share your name, then in turn three you share your employer details, and then in turn five you shared your salary. So each one alone is harmless, but together they create your entire identity. So Camp will track the entire session, not just the single current message that we are dealing with. Then agentic, because this is built for the way AI is actually being used today, where we have multi-turn conversations, agent pipelines, memory-aware systems. So it's built keeping the modern system with modern risk at its core. Then we have the masking. So instead of hiding data with asterisks and labels, as we have seen in the current approaches that are out there today, uh, what we have done is like we have replaced Campbell, replaces those entities with the real identities with consistent and realistic fake values, so that LLM can get a complete context and meaning of the query, but just with a different name, a different city, or a different bank account, different bank name, location, etc., etc. And then finally we have pruning, because something, let's say like something is too sensitive to pseudomize, like social security number or an account number. So Camp will, remove it entirely before it even reaches to the model. So we have these four high level layers, and together, they create one module that solves the data leakage problem while, keeping the utility and the usefulness with models. So moving ahead, what exactly is CAN? So it's a lightweight Python module. We can call it as a middleware layer that sits between users and AI agent. So whatever the conversations we are passing it, it needs to be passed from the CAMP. so that camp will analyze the queries and removes all the sensitive information, and it will replace it with the similar but the fake information, and then it will pass it to the AI agent. Now, again, like it will take the response from the AI agent, and it will demask all the fake values with real ones, and it will send it back to the user. So it watches your prompt for each turn. Then it understands when multiple pieces, together become risky. Then and then only it will intercept. Let's say like if you are just passing the name, then it won't consider that as a risky. As in today, passing the name to the LLM is not a huge risk. As in we need that models should understand us so that it can provide us the better personalized responses. Then it keeps like it protects. It rewrites the conversations with safe and similar identities, so the model can still use like real values and reason properly. And as I just mentioned, that finally it will restore and give the user real output back, so nothing breaks from their perspective. So considering two perspectives over here, user and model. So from user's perspective, nothing gets changed, but from the model's perspective, model never saw the real data, but still produces the good responses. Now, if we talk about the camp, where does it sit? So, camp sits between every risky data exchange that is being done in the entire pipeline. So, let's say like whenever a user talks to an AI agent, the message first passes through the camp before the message reaches to the LLM. Camps check whether it contains the sensitive risky information or not. Then again, like when agent talks to the APIs, database tools, or even with other agents as well, then in the middle, like it demasks the things, query the DB, and again mask it and send it to the agent. So camp will sit wherever sensitive data moves between user, AI agent, tools, APIs, and other agents. So it acts like a privacy checkpoint for the entire AI workflow that we are having. Now, let's see like what's inside the camp, how it's built. So going through all the thin layers before we demo. So the first component is extractor. So it's basically built on top of Microsoft Persido, which is an open source library from Microsoft to detect sensitive entities from text. And together with that, like we have extended it with custom detectors on top of it. So together it can detect 28 plus sensitive data, including PII information, financial data, salaries, and etc. etc. And two things that makes it different in practice is it understands the context really well. Like if we have Austin, Texas mentioned like this in query, then it will consider that as a one location, not two separate things. And second thing is like it reduces the false positive. So not every number is an account number. Not every name would be sensitive. So the extractor is smart enough to know the difference. So by the time a message moves from this layer, we know exactly what's inside the messages, what's been detected, and together with that, the type of entity, as you can see here in the example. Then comes the second component or second layer to it, which is session registry. So every time the extractor finds something sensitive, it stores it here. What type of entity it was, what was the actual value, and in which turn it appeared in, so that the session registry can make this camp stateful, and it holds the entire picture of the entire session that you are having. Um, like important thing to notice over here is like it's how it's built is um, it lives in your memory itself. So nothing is written to disk, nothing is persisted or never set anywhere. And second thing is like it's scoped to one session. So whenever the conversation end, it will just get vanished. So again, from the new session, new registry will be created, and everything will be stored as a new. So camp always knows like what's been disclosed, even if user revealed it 5 turn ago. or after, or anywhere in the between of the conversation. Then third component, the co-occurrence graph plus CPE scorer. We can consider this as a brain of the camp. So let's say like once the session registry has collected all the entities, then this component takes those entities and then it determines that if we combine, let's say all the entities, how risky is it? And it will, provide the scores as well. So look at the graph over here. So on each node is, a type of sensitive data like person, organization, account, salary, and the location. And the line connecting to them represent that these pieces, appear together in the same conversation. Now, the key thing to note over here is like the more connection a node has, the more dangerous, it becomes. So let's say like an account number that is connected to a name, a bank, a location, and a salary, so that will create a complete, identity of a person. But let's imagine that account number is far more. So over here, like account number would be far more dangerous in context of person and other details. But let's say like if it would have appeared alone, then it won't be that much risky. So Camp, knows that let's say like if account number is coming alone without any context, then it's not that much risky. But again, like things like account number, like we have kept that risk score higher so that it will, block. So such things are, blocked by the camp itself. And that's what the formula over here captures as well, that the end, like amplify means, let's say like taking the entity and multiplying its risk on how many other sensitive things have connected to it. So more the connection, higher the multiplier would be and higher the amplifier would be. And the CP score, this is the full formula at the bottom, just adds up all the risk of every entity in the graph, and each one, amplified by its connector. So we can consider this as a threshold level as well, which we will gonna, understand much more in detail when we will just carry on the demo. Now, the fourth component is pseudomizer. So this is where actually, protection will happen. So the moment CP score, crosses the threshold, sorry, crosses the threshold, this component will comes into the picture. And this doesn't just, mask the current message. It goes back to the entire session history and it will rewrite the entire conversations every turn from the beginning. Now, how this is actually being built is like it will create the fake identities. So, in we use a Python library called Faker. It generates realistic synthetic data, real sounding names, real sounding cities, real sounding, bank names, and all those things. And it works at the value level. So not the sentence level, not at a message level. So it finds the exact entity, let's say like Michael over here, and it will replace it with the James, and so on. Like over here, we have this bank name. So it replaces with the synthetic bank name, and we have this account number. So it, strictly blocked with that account number. Then we have this, Austin, Texas. So again, like it replaced with the fake and synthetic detail over here. So when the LLM reads the rewritten conversations, it reads a coherent story of what has been, changed, so that it can, still reason properly. It just don't know like who the real person is, what was the real bank, and etc. etc. Now, this is the fifth and the final component, that is demasking layer. This is the last step of the entire, round trip. So at this point, the LLM has done its job. It processed the conversation. It generated a response, but everything it saw was fake. Now, before that response reaches to the user, Camp will again, intercept, and it will scan the response for every fake value. It placed and swapped them back to the real ones. So using the same mapping that we have built during the pseudomized step, it will just perform that step, but in the reverse order. So look at the table on the, right hand side. This is the complete round trip. The user got the perfect, helpful response. The model, saw something named with identity James, but again, user is receiving the identity with Michael. And here again, a few things to notice. it handles the overlap very safely. So consider like if a fake name appears inside a long phrases, so it will always replace the longest matching values first to avoid partial replacement. And when the session gets end, the entire mapping will be wiped off, as we just discussed in the session registry layer as well. So that's the complete loop where real data will always goes in, protected data will always goes to the model, and again we will be getting the real data for the user. Now moving to the demo. So like I have this entire Streamlit application that will initially show you the entire process. Then we will just go ahead with the individual components and the features of the camp. So here you can the CP threshold that we talked about. Here you can tweak the CP threshold of what value you have to cap. This alpha co-occurrence rate, after so many testing, like we have finalized this 0.30, but you can change as per the use cases that you are working with in any regulated industry. Here you can specify the block list as well, what entities you need to completely or entirely block from getting it exposed to the LLM. So let me just try one prompt over here. So the prompt says, can you just help me draft the email to my college friend? Here we are exposing the name. He works at Google. We are exposing the second entity, and we haven't spoken in while, just to catch up. So let's just send, and let's see what camp detects over here. So this was the turn one. Here it detected two entities. First was the name with 85% confidence score. Second was the company organization name with again 85% confidence score. And together, these two, they created a graph, and their combination itself, have a CP score of 1.17. Now 1.17, which is less than the threshold that we have set. So it will send the exact message that we have sent to the LLM, and LLM generated us the response, and we have the exact names what we have passed on. Now let's say like I forgot to mention that I have also forgot to mention that I moved to SF and started a new job as a PM. So here, like I'm exposing the location where I have moved, and I'm also mentioning the salary that now my new salary would be this. And I'm just asking to meet up on sometimes to the David. Now let's see what happens in turn two. So you can see in turn two as well, it detected this San Francisco as a location, and the salary with 65% confidence. This is some financial amount, right? So now together, all the entities like they crossed the threshold that we have set. So now camp will intercept over here. It will rewrite the entire conversations with the fake synthetic value from the beginning. So in the beginning, if you remember, like we have this friend David, but now it has changed to Allison, and it also changed the location. It also changed the financial amount that we have provided to it. And then LLM generated the response to us. And then finally, what we will see as an output with all the real values that we have provided, like David, Google, San Francisco, and the salary that we have provided. So this was the quick overview of how camp will intercept when the CP threshold will cross, and how it will replaces the identities with the fake identities, and what we will be getting at the end of the response. Now moving to each individual features that we have at a camp. So the first one, like Streamlit, we have seen the entire end-to-end life cycle of the camp, where it replaces the fake identity value. Now, let's say if we need to install the camp, so there are a few ways we can install the camp by just running this pip install camp. It will install the Campy and we can directly use it. Currently, it's been supported in LangChain and agent framework, so we can install the specific version for that specific agent framework that we are working with. So these are the three ways we can install the campaign. Now, how we can implement that with agent framework. So you just need to, import the camp from, you just need to import the camp masker from the camp and just create an object of it where we need to pass the CP threshold initially. And another thing, like we can have the reduction mapping as well. So let's say like if you get any SSN, then just blocked it. But let's say in some of the cases, we need some, personalized response from the LLM. Like if you just pass the blocked, then LLM might say that your SSN was blocked or something like that. So we can, add the numbers over here. Like default this SSN, you need to take whatever the SSN users provide. You just need to ignore that. So it will just replace that with whatever the value that we have provided over here. And then this is the message. Then with the Microsoft Agent Framework, we have created one agent over here. And before creating the agent, we just processed that message that is coming from the user from this masker that we have created. Now, this result will provide us a lot of values. So it will provide us what we have to send to the LLM. It will also provide the decision that Camp has taken after carefully, reviewing this entire message. And it will also reveal the CP score as well. So like we will send the message that result will provide us that we need to send to the agent. So from that, like we are capturing this property and we are sending that particular message to the agent. Then agent will, run and it will provide us the raw response back. And then finally, we will just use the demask response function from this masker, and it will demask everything and provide us the message that we can, pass it on to the user. So I'll just execute this, see, and let's see what it responds to. There is something wrong, I think. I think it's not working. Like I've tested it before it worked, but let's skip this. I'll just come to this piece at the end. But let's move to the another thing that I wanted to highlight over here. So let's consider this. What all are the decisions that Camp can actually take? So let's say considering three cases over here. So Camp can either pass the message, it can either block, or it can either pseudomize the response. So let's say like if we don't have any let's say if we don't have any entities or any sensitive values in the message, then it will completely pass that message to the model as it is. Or let's say like if we have some highly sensitive information in the message, like SSN number that we have over here, then it will block that particular sensitive information or the value. And last one, it will pseudomize. Let's say like if we have a few sensitive information and together they create a risk and that crosses our threshold that we have set, then it will pseudomize all the value with the fake realistic value. So let me try execute this second demo, and hopefully uh, that produces us the result and show us the results. So yeah, here like let's say like inside we have sent this, and as we don't have any entities that are sensitive, so it will directly pass it to the model. And here like here we have SSN number, so it will block that. And in the last case that we have few personal identifier information, and together they created a risk. So again, like it in the camp will intercept and it will rewrite all the value with the synthetic value that we have generated. Now, camp is not just limited to, PII informations or some sort of identities or some sort of entities that are already there. And it's not, limited. We can, teach it to detect anything specific to your organizations. So let's say like if you are dealing with something sort of employee ID a lot or internal project reference a lot, so that so here you can, create a custom patterns as well. So, like employee ID would always appear in this particular regex pattern, and you can provide a score as well that if that occurs, then this would be the score. You can score from 0 to 1. 1 would be the highest that we generally use for SSN numbers, account numbers, and highly sensitive, which will be blocked by the camp. So here we have created these custom patterns, and we are providing custom patterns along with the reduction mapping that if it founds any employee ID, then it just replace with this particular value. And then I've created this message where we have the employee ID, working project reference ID as well. And we have this email as a sensitive information. Now let me just run this and show you the result that we are getting. So, the decision that CAMP took was to pseudomize as in the CP score crosses the threshold. We have set the true threshold over here, and the CP value was 3.80. And the detected entities were, email address, internal project reference, employee ID, and the person name. So this was the query that was received from the user, and what was sent was it replaces the name, it replaces the employee ID with what we have provided as a reduction mapping, and also we have replaced this project reference as well, and it replaced the email address of that particular David to Johnson, which is again a synthetic value generated by a Flickr library. Now, we have also designed this camp to, like work inside the tool calling pipeline as well, where the LLM doesn't just respond, but it calls the real backend system. This is the, agentic use case that we can say. So over here, like I have defined this tool internal within this file as a JSON. And again, like we have created this camp masker over here, and we have provided the threshold value. Now, here we are like asking that I'm Sarah, and this is my mail. This is my claim insurance. I just need to fetch the claim insurance from the tools that they have that we have attached over here. So again, similar workflow like we have created. We have created the masker. We have passed the message from the masker, and we have called the LLM. Now, whatever the results that we will be getting from the LLM as a tool result, we will, again, like I have written all this line just to show you what internal process CAMP actually does. But with this one line, you can, call the tool that will, mask the content, that will demask the content, that will call the tool. And again, it will mask the content and send it back to the LLM. And the final response, again, we are sending the tools and the tool result that we will be, appending over here. And whatever the result that we get after tool calling, we will again demask that, and them, and again we will provide it to the user. So if I just execute this demo file, then you will be able to visualize better if as we have all the logs that we have placed. So this was the query that we have received. Now we based on the CP score, we like generated the faker synthetic data. We pass it on to the LLM. Now LLM will opt for tool call. So it will provide us that we have this claim ID and the customer name is Javier Johnson, which is again a false value. We will internally demask the tool result that we have received from the LLM. And after demasking, we call the tool. And this is what we got from the tool result. We again mask the tool result, as in we don't want to expose this data to the LLM. So we again remask that. We send it to the LLM. LLM draft the response for us. And then after drafting that response, we again, demask and provided back that response to the user. So this was the entire, agentic use case that can be implemented across tools, MCPs, and a lot where we are implementing agentic use cases. Now, let's say like we have all the demos that we have showed as of now are something that was working on a default values that we have set, but you can tweak the values as well as per the use case that we are working in. Let's say if it's a healthcare or finance use case, and that customers are like sensitively and they are regularly exposing some certain informations on a regular basis, and we need to intercept camp over there as well. So for that, you can change the weight of the entities as well. So in the first object that we have created, like we have created it with the default values, and the second object, like we have like added this entity weights as well, where for person, email address, and for phone number, we have set that weight to the one, which is again max value. And then we ran the camp against both the things with the same threshold of 4. And if we'll just see the result, the first one will pass that query directly to the model, as in it doesn't process the threshold. But the second one, where we are dealing with the specific use cases, whether it could be healthcare, finance, where we have increased the entity value. So over there, it will intercept and it will pseudomize the value before passing it. And now the last use case, whatever the decisions that camp takes, it will as we have discussed in the thin layers, that it creates a co-occurrence and CP score graph, and based on that it decides that whether we need to intercept or not, whether we need to protect the data or not. So using the results that we are getting over here, like we can, so the masker that we have created and the results that we get over here, we get the graph as well. So here masker.graph.graph will provide you all the coordinates for the graph. And again, like we have written all this code to plot that graph beautifully on matplotlib. So I'll just show you this graph. So all the entities that we have exposed in the message, it will internally create this graph, and it will keep track that, okay, in turn 3, the CP score was crossed across the threshold that we have set, and at that time camp intercept and it performed the protection layer that we are trying to intercept. So we get that entire graph picture as well over here. Now this was all about flexibilities and the control that we are getting over camp. Now moving to like should we trust the camp or not? Like let's find out that how do we trust this, and does camp actually degrades the quality of the response, or if we are replacing real data with fake data, does the model still gives us useful answers or not? So for that, like we have tested and evaluated this, camp module with 500 prompts across 4 different domains: healthcare, finance, hiring, and general purpose queries. And for each of these, like 3 conditions for every prompt. Like first one is the row, where we pass the query directly to the LLM without any protection. In the Pursudo, like we use directly Pursudo library from the Microsoft and try to remove the entities from there. And third one is camp. So sorry. So as we measured how similar the response were to the row baseline using cosine similarity, and how close the response is to the row responses that we were getting. And the closer the response to the row would be, the better quality is preserved. That's what we that's what we believe. And honestly speaking, like in the beginning, camp was scoring way behind, as in the response were drifting too far from what we would expect or what we would get without protection. But after a few refinement to how we pseudomize, how we preserve the context, the numbers got significantly better. So look at the overall average as well. For row, like we have 0.892, that is your baseline. For pseudo, that comes to 0.839, and camp lands at 0.813. So yes, there is a bit gap, but it's really small and acceptable gap for the level of protections that we will be getting. And if we check the domain breakdown, so healthcare, where the patient's information and medical context is involved a lot. So camp actually outperforms the pseudo, and it was able to detect the PHI informations and a lot of things. In general conversations, it's very close to pseudo, but in finance and hiring, it like we have a slightly larger gap, and the gap is mostly due to the dates, as in camp detect the date, and it will replaces with the date that are no closer to the context that we are passing in. So in general conversations, it's very close, but in finance and hiring, we are still the areas where we need to still refine it. Now, like enough of good things. Let's talk about where camp fails short or right now needs to be worked on. So first of all, like it's not for every industry. Talking honestly, because this use case it's designed for highly regulated industries where data is so much sensitive and costs us a lot, as it adds a latency as well. So not suitable for latency sensitive deployments like customer supports or voice assistants. And currently, no files or document support as of now. It's provided via this module. This is something that we are working on it, but these are the real gaps, and they are still exactly we are trying to work on it, and will soon be releasing in coming days. So yeah, that was if that was the camp, the problem data leakage that we talked about is very real, and camp was our attempt to solve that without breaking the utility, without changing the model, without adding or without sending your data anywhere outside of the boundaries. So if you want to try it out, I have attached the GitHub link, an actual research paper where we have all the details of it, where we have all the details of it. And yeah, that was it. I mean, if you have any questions, I have this my social handles. You can try to reach out to me. Let me just go to the last slide so that you can scan, and we can connect over to the socials. Uh, yeah. Yeah, thank you for your time. So let's open it up for the questions if we have any.
All right. Please post your questions in the chat or raise your hand. I'll enable your speaker. Right. We have
Yes, okay.
Swapnil. Yeah, yeah, Swapnil, you already have speaker. Right.
Yeah, thank you very much. It was really great and informative session. Of course, as you said, we have to think on implementing camp-like protections for our all agents and conversations. Of course, highly regulated industries only would like to have it, but that is a good practice to have it. I have a question. How can we have it integrated? For an example, I mean, I saw you created some code and you were running it onto the local host. What if I'm building one agent in Azure Foundry and I want to apply this camp guardrails or protection to my agent? How would I do that?
Okay, so
How can I
basically,
provision that code?
yeah,
Yeah.
I got your point. So let's say like if you are building an agent in Microsoft AI Foundry, now there will be some sort of interface where from where you'll be calling that, right? It could be either Python, it could be either C Sharp, it could be either any sort of interface from where you'll be calling. It could be some sort of automates as well. So at that point, the camp will be placed as a boundary. So whatever the query that are going in, it will first go through the camp. and then it will reach to the Foundry agents that we have created. In general cases, like let's say if you are creating agent in Microsoft AI Foundry, so we won't be, directly giving that access to the stakeholders in a practical scenario. We'll be having some sort of, interface. So at that place, camp will be, generally sits there.
Sorry, interface means, I mean, are you exposing any APIs which can be configured before we actually hit for an example, user is asking some questions to, and that question is being passed to the LLM in Azure AI or in Azure Foundry agent, for an example. So how we can have this attached? I mean, are you saying that this code is exposing some kind of API or creating some kind of wrapper? I'm a bit confused. I'm sorry.
Yeah, so basically it's a module. So let's say like if you are using any sort of agentic framework, right? In order to build the agent, in order to call the agent. So like before passing in the query from that agent frameworks, at that time camp will be helpful, and we can keep the camp before it intercepts the model or agent. So this is basically more of a technical tweak that we have to do while we are building agents using agent frameworks. Uh, I hope that answers your questions. As in, it's not something that we can plug in directly into the Microsoft AI Foundry, but whenever we are calling that agent which is created in Microsoft AI Foundry via some agent framework, at that time we can place this as a a boundary before the agent where we are calling that agent.
Right, right. For example, I think it could only be applied to the agent which we create through code, or we saw code agent,
Yeah,
right?
yeah, that's
Okay,
true.
got it. Anyways, thank you. Thank you. I got my answer. I appreciate it.
Yeah, thanks.
Right, anyone else? Okay. So I think let's conclude this then. Thanks so much, Aman, for this session. And this brings us to the finale. All right. So it's been a power-packed day, starting right at 9 a.m. through the day. Thanks to everybody who joined. We had almost like 80 people tuning in from, at running participation levels. So having that many people out on a Saturday, it's always delightful to see. And then hearing from so many learned people through the day, so many interesting topics. We learned through a stack of topics, right? A host of topics, I would say. And I'm sure whoever joined is taking away something or other. It was really interesting in terms of conversations today. Audience was really, really interactive. Thank you all for excellent questions and staying engaged throughout the sessions. Thank you so much for joining. It's been a wonderful, wonderful day. And we had the pleasure of hosting this. So from Delhi Tech Community, Hyderabad User Group, and all the organizers, I would like to thank all the speakers who joined us through the day. Thank you all, and let's keep the community voice going. Have a great rest of the weekend.
Thank you. Thank you so much.